When Akira asked me to speak, I asked him, "What do you have anything you want me to speak about?" And he said, "Something very technical." And I said, "Okay, I can do that." So this is going to be very, very technical. So there, everyone should raise their hand at the end. I should probably lose everyone at some point. So, um, uh, as Akira was saying, my name is Evan Phoenix. I go by Evan PHX most places on the internet. I have created many Ruby things, such as Rubinius and Puma and Benchmark IPS, which I was very happy to see many people using in presentations. I am a Ruby Gems and sort of by proxy C Ruby committer. I am the CEO of a small startup called Vectra, director of Ruby Central, and I also function as the rubygems.org accountant, which means that I pay the bill. Thank you. Thank you. I live in Hollywood. This is what it looks like from my backyard. No, it does not. With my two daughters and my wife. And I wanted to say it is a very big honor to be here giving the final keynote. So I wanted to say thank you to all of the organizers. And I'd like to have everyone give the organizers a big round of applause for a great RubyKaigi. I felt as if I was giving a very technical talk, I should list my credentials. So these are my credentials for this very technical talk. Many years ago, I did a fork of Ruby called Sydney that was added native threads. I have built a fully parallel Ruby implementation that has a dynamic JIT in Rubinius. And in fact, Koichi-san is who reminded me of Sydney just today. I had almost forgotten, and I was trying to, I was thinking, am I getting that old that I had forgotten? And I realized why I had forgotten. I went back and I found my original email. It's because it was 10 years ago. This is from 10 years ago, an email I wrote about my fully parallel Ruby implementation. That I honestly could not believe it had been 10 years. I thought it was very interesting looking through all of the mailing list thread from 10 years ago, and I found Nobu-san being very, very nice to me and helping me out. In fact, he did not know at the time, but he saved the only copy of the implementation of Sydney in the mailing list on accident, because this URL still worked at the conference today, and I went to go look at it because I hadn't looked at it in probably 9.5 years. I did not remember how big the patch was. If there was any reason why it was most likely not ever merged into C Ruby, it's because it was a 500 kilobyte patch. So if you ever send Nobu a patch, do not have it be 500 kilobytes. So Mats has said a few times here, as well as at RubyConf, that Ruby 3 will be 3 times faster than Ruby 2. And at RubyConf, I don't know if he had announced it before then, but that was the first time I had heard it. And this was my natural feeling about hearing that. But then it turned very quickly to, but how should we do this? If that is our goal as a community and as Ruby core and everybody who loves Ruby and wants to help, how could we do this? So that is how I thought about what I was thinking about when Akira asked me to do something very technical. So I composed this talk on that topic. So what do I want, hopefully, you all to get out of this talk? What's my goal? My goal was to convince you that C Ruby needs to have a just-in-time compiler. and that we will not get to Ruby 3 without one. Also, that now is the time to build it. We've done many things in the community and we've played with many directions, but now is the time to actually act on this. But that also, we must be pragmatic with our approach to getting a JIT compiler. So, part one of my talk, performance. So what is performance? It's important when Matt says it is 3 times faster, we have an idea of what performance actually is. Performance is usually boiled down to 2 things. Either you do the same amount of work, but you do it in parallel. So if I get 3 web requests and I do them one and then the other and then the other, or if I do them all at the same time, that the second one is 3 times faster than the first one. Or if to accomplish something takes 1/3 the amount of code, that is also 3 times faster. But they both achieve 3x. And Mats has talked about this in looking at parallelism as well as algorithms and that kind of thing. Let's talk about parallelism first. With CRuby, parallelism is much harder than running less code. Having written a 500 kilobyte patch to attempt this, I can tell you that that's true. The core library, which is I refer to a number of times, which is all of the methods that you love to use in Ruby, all of the methods on array and string and enumerable and hash, all the things that you think of that make up Ruby are what I call the core library. And they were not designed to be run concurrently. They do very normal things that a programming language should do, but they do them assuming that that code is right there, the only one that's able to make those modifications. And changing that is a very big task. And so Mats has sort of proposed a couple of times adding strange parallelism mechanisms, such as actors, which maybe have no shared memory between them, which for a Ruby programmer would be very, very odd, or using things like streams. But all of them force users into very strange and unfamiliar places. That's not to say that Ruby can't change, but those things are very unusual to most Ruby programmers. And they're not small changes to try to accomplish a lot of the parallel goals either. They would touch almost everything in the core library, or they would introduce these concepts that would confuse users. So as we talk about doing less work, a lot of times, and it's been brought up many times at RubyKaigi, we talk about how can we improve the code, how can we make it faster and do more things, and most of those are micro optimizations. Those are great, and they can do a lot for us, but I feel it will take a very long time to get to Ruby 3x3 if all we make are micro optimizations. They only very slight, small changes that change one tiny little piece everywhere. That being said, they're a good place to start. And there are a number of easy fixes that I would hope Ruby Core would look at, and anybody who would like to contribute. One of them is there are a number of missing caches within the core library. Every time that you see a call to RB func which are 364 of them inside the core library, all of those are slow. Every single one of those could use a cache on them. And doing so could improve a lot of performance of a lot of different kinds of code. But unlike micro optimizations, I feel that we need macro optimizations. We need something that can be applied to a lot of things and can make a big jump. And to make those big jumps, sometimes we need bigger ideas. Now, a JIT is not necessarily a revolutionary idea, but to put one inside C Ruby and in the way that I'm proposing might be a big idea. So a JIT lets us run less code. And I believe it is our best bet for getting to 3x faster. We can do things such as using caches to understand better about how the code works. We can emit better kinds of code. And it has been said here that perhaps Ruby is too dynamic to be used for a JIT. And I think that is not true. Ruby is no more dynamic than really Java or Smalltalk. The low-level pieces are just as dynamic. So when I talk about dynamic, everybody thinks of Ruby as being where everything can change all the time. And that's true, but in fact, and I've done these tests myself, most places that you call methods within your code don't use polymorphism. Most places call the same kind of method, the same kind of class every single time that they're used. So let me give you a quick example of when you have monomorphic calls, what can you do? So here's a very simple piece of code, which, that is not a great way to do an exchange rate. I do not suggest you use this code in production, but it will serve fine for our test today. And you can see here, the great thing about a JIT is that it does what a human would do naturally by looking at the code. So everybody can see that, well, we're using this fetch rate call, and we've got the method right there, and it returns a constant. So why don't we just use the constant? And that's exactly the kinds of things that a JIT compiler will do for you. And so maybe also that we've actually called it with a constant like this, and that's also great. The JIT compiler can see all those constants, and it can do all of the work to move that data around and to evaluate those things at compile time. And so something that was a few method calls, and a few math operations, division being not a very fast one also, is now something that takes no time. So this particular code is probably 1,000 times faster than the original one. And those are the kinds of big jumps that allow us to get to 3x faster across the board. And that sounds great. But how do we get there? Like, how do we build a JIT compiler? What does that actually look like? So there is a lot of research on this, and I thought I would run through a little bit of it so that we all have an idea of what that looks like. So this is part 2, a survey of the past. I'm going to start with a language called Self. It was the child of a brilliant programmer named Dave Ungar in 1987. So just a few years before Ruby came out, they had developed a JIT compiler back then. And Self was very uniform. The only thing you could really do is call a method. There was no local variables. There was no instance variables. You could only call methods. And the only way that it was fast was because there was a JIT compiler that could remove all of those dynamic features when you actually were trying to run it. So it introduced a lot of things that many of you have seen or heard about here at RubyKaigi, such as polymorphic inline caches, which is a way of speeding up method dispatch. It was the first one to drive a lot of compiler decisions from those caches, so those caches became profiling information, not just a cache. And the paper, which I should have included a link here to, the papers all about Self are wonderful. One of them talks about how important method inlining was to actually do this, and we saw an example of method inlining just before. So like I said, the self JIT was the only reason that self was an actual language that anybody could use is because it had a JIT. Otherwise, it would have been far too slow to actually use. And it did also things such as inlining blocks, which I think if you were at the JRuby talk, there was discussion about that, which made things like in self there's no control structures, much like Smalltalk. So all usage of, say, an if or a loop was actually using a block. And so inlining blocks became very important to make even the most basic tasks work at all. And most importantly, it also did things like inlining primitives, and we'll talk about that. That's actually a very important key part to my talk today. So self, if you talk to designers and you look at papers, you find that the work that was done in self is the foundation for virtually all dynamic language optimization that you see today. There's very little research that does not point itself or have its roots in the work that Dave Ungar and his team did. And all of the lessons are still very important, such as it was a proof at the time in 1987 that a dynamic language could actually be fast. That was not necessarily something, or at the time there wasn't really any work being done in production in dynamic languages. So it was a good proof to the industry that, hey, we could actually do this. And the key part there is that the performance is derived from removing the dynamic aspects of the program when you're actually running it, by seeing what it does as it's doing it, and then removing the dynamic aspects. We move on to the next one, which is a language called StrongTalk, which is also very interesting given Matz's discussion about adding types. It was an idea of taking the work that had been done in self, and also the idea of the team was interested in having a type hierarchy that fit in with Smalltalk. And how would those things work together to make them fast? A quick diversion from the performance talk that I found very interesting is, I know this morning there was talk about Matz's not making any headway on soft types, which is fine. But I thought it was very interesting, given all that what StrongTalk types look like. They were a type hierarchy, much like you would see in Java or whatever that actually had, or that you see at runtime in Ruby. And it was there only to help developers understand the code. It actually made the code slower to run, because all of the points in the code that would have checks to say, make sure this is a string, a lot of those would have to be run at runtime, so you were actually slowing the whole thing down, which is an incredible thing to look at, to think about. That meant that the runtime, the parts that actually made StrongTalk fast, were not because of the types. In fact, the types just made it harder to do, and they were still able to make it very fast. Like I said, they slowed it down, and by introducing guards, and they were only there to help. The StrongTalk team had come from the self team. There was a number of engineers there, and they were there to apply, like I said, apply the research that they had learned earlier, such as inline caching and method caching. And where it is, the StrongTalk is still a thing today. But the most important thing that happened to StrongTalk is that before the company actually released anything, they were bought by Sun in 1997 to turn what they had built into the Hotspot VM. So the Hotspot VM, as it existed originally, was to run Smalltalk. It was to run a language not unlike Ruby, which is itself a very interesting history lesson. So the lessons that we learned from StrongTalk were that gradual typing is possible, but it doesn't improve performance. It can be nice to have to help people understand their code, but if someone tells you that, oh, if only Ruby had types, it could be fast, the types will only make Ruby slower. you have to compensate for the types with other things such as a JIT compiler. And obviously it was building on more of the self-research and showing that those techniques could be applied to other avenues and other kinds of languages. So we fast forward a bit, probably 10 years or so, to V8, which is another very interesting virtual machine that we can learn from. You all know of V8 mostly. It's the JavaScript engine inside the Chrome browser. It was started by Lars Bak, who, not coincidentally, was on the StrongTalk team and on the Self team back in time. And so you could see again a line through of people bringing all of those techniques forward. And I have a little funny aside there that I guess someone asked Lars where the name came from, and he said this was the 8th time someone had asked him to write yet another dynamic language VM. And so he decided he couldn't come up with a name, so he just named it version 8. So in other words, V8. I don't know if that's true. That's just a rumor. The optimizations that you see V8 having is things like fast property access with hidden classes, which we can learn from pulling things in, not storing everything as hash tables, although Ruby 2 doesn't do that anyway, but it's still a very interesting technique. It also used tiered compilers. One thing I think that we learned from V8 that I didn't include on here is that unlike SmallTalk or StrongTalk and Self, JavaScript has to run fast because the user is right there expecting feedback immediately. And so the use of tiered compilers shows us that we can make a JIT compiler that will work for Ruby that won't slow it down if I need to just run -e something something something, but it can sort of make the code faster over time, and it doesn't require an upfront slowdown. Right? That's important to know. So as we look at all this, our quick little survey, we see that the JIT technology that has been put into all these different languages was the main driver for performance. Now they all made micro-optimizations for different pieces over time, but none of them would be mainstream, including Java, if they had not had an actual JIT compiler that was removing a lot of the dynamic features and making it actually fast. So that's the main result of this survey. So when you're building a JIT compiler, as we're doing right now, basically, you have a couple of different options about how you would build a JIT if you've decided to build one. And let's go over those just briefly. There's 3 primary techniques you can use: tracing, a method JIT, and sort of a general partial evaluation. And these overlap with each other, but they're generally terms and pieces that are used to describe different kinds of techniques. A tracing JIT is triggered when somewhere in the code has been run often enough. Many times that's the top or bottom of a loop. That's a very common place for a tracing JIT to come in. And the minute it decides to run on, say, the 1000th time through a loop, it will start recording everything that it does. And that record of everything that happens is recorded without branches. So it's a straight line piece of code without if statements. All of the places where something could or could not happen are replaced with guards, so that either you go down this very fast path or you just don't bother at all. And the problem with tracing is that if you look at a piece of code, within a program there are effectively an exponential number of paths through that code. If you've ever done code coverage, I believe it's either C3 or C4 is the idea that you have done code coverage on every possible path through your program, which is if you run the true half of this block, you run the false half of this block, and you run all of them. And that's just the exponential combinatorial explosion of paths. And as a result, you get this huge number of traces to manage. And because you've got managing all those traces, you have to be able to exit the traces very quickly in order for the performance to really work at all. So trace management becomes important. One of the other things that I found interesting is that the branches are there, and the not doing certain branches of code are there with the idea that you want to do things as fast as possible in a straight line. But a lot of times in processors that we have today, branching and moving around is itself very cheap, so that kind of trade-off within a tracing JIT is not all that important. In fact, I'm just going to skip that slide altogether. The next one is a method JIT, and that's the one that people typically think about. You have a method from a def to an end, and you're going to compile all of the code within that particular method. And you're using the type information that perhaps you've saved previously with other runs inside the interpreter or whatever it might be. But you've made this decision, and you're hopefully going to have some information that you've stored elsewhere. Unlike the trace JIT is using the information as it comes up right there, whereas a method JIT has saved the information in the past, and the profiling information is going to use it. Well, there are some problems with method JITs. The bigger the method, the bigger the compile time. The JVM, is a good example, has a limit on the size of the method just because of how big it could be. And as you inline methods into those things, they get bigger and bigger and bigger and bigger, and again, your compile time goes up, so that becomes an issue. And in usually where people start is if you have compiled a method to machine code, and now you're running it in a loop, the only time that machine code will kick in is the next time you call the method. Or you have to build into that machine code the ability to exit a loop or something like that into the machine code, and that's possible. The JVM does this. It's called on-stack replacement, but it adds more complexity. So it's something else that you have to do within a method JIT. The last one is called partial evaluation. If you saw the truffle talk here at RubyKaigi, they talked about partial evaluation, and I wanted to bring it up because it is a little bit different than method or tracing. Usually, in this particular case, I'm talking about truffle here that uses a specialized AST, and it attempts to, based off of how things start to lay out, compile bits of the actual AST, independent of whether or not they might be in a method, into code to run them. They can have some slow startup, and there isn't a lot of widespread work around these. None of the StrongTalk, none of them use partial evaluation, so there isn't necessarily as much literature to learn from. But one thing we do find as we look at these three techniques is that most virtual machines are moving towards method JIT. One of the most prominent tracing JITs was the original Spider Monkey that was inside Mozilla, and it was actually removed, and they use a method JIT now because they could get better performance out of it. There's really only two main tracing JITs that are in widespread use, which is LuaJIT and PyPy. So we see that the more times you have to exit machine code and the compiled code, the slower something is, and that's one of the problems with a tracing JIT. But one of the most important things that you can get from a compiler, and that a compiler needs, is as much code as it can within one large swath that it can see, and we call that typically the horizon. How much can the compiler see at one particular time, and therefore how much can it optimize within that boundary? And the smaller the horizon, the less work it can actually do. So let's look at a quick example. So if you want to have as wide a horizon as possible, given this code, we're going to quickly turn it into a pseudo bytecode here. We would see something like this. And in this particular case, this is not this does not give us a very wide horizon. If the compiler is looking at this, it really sees almost nothing that it can actually optimize. But if you allow it to, if you do some inlining and you allow foo, the constant within foo, to replace it, you have now widened the horizon. The compiler is now able to see, oh, look, you're adding two numbers together. I can probably do that right now. And now you can actually apply some optimizations, whereas you couldn't before. And I bring this up because it shows a very particular problem about adding a JIT to CRuby. So we've taken 67 slides to get to the meat, the real bit of about this talk, which is that all of CRuby is, all of the methods are written in C. All of the array, all of hash, all of the enumerable, all that kind of stuff. And all of those places that exist are a problem because they don't allow any kind of compiler that runs at runtime to be able to see into them. They are black boxes. And so you're not able to optimize any of them. And so what I'd like to do is propose what I'm calling the canary. So from a saying in English, the canary in the coal mine is the thing that you use that indicates to you whether or not something is happening. And I'm going to propose this as people are thinking about Ruby 3x3, and this is actually not mine. I took this from, I believe, a truffle paper or somewhere like that. That this code, I would like this code to be submitted as, it's a very short little snippet, but if we were to achieve Ruby 3x3, then any sufficient compiler should be able to turn this expression into the number 1. And doing that within CRuby is exceptionally difficult. But we're all going to do it right now, if you're all ready. So what we do is we find this as the bytecode. And obviously, as a compiler is looking at it, it would say, oh, look, I'm making an array, I need to call min. Let me go look up the definition of min. Oh no, it's in C. Nope. So I've put our exercise at the later on, so we've got one section first. So given all of that, and I've now hopefully convinced you that we need to have a JIT, and what could that JIT do for us? So let's look at some other, you may ask yourself, well, why not use something that already exists within the community that we could just switch over to? Maybe like Rubinius. Now, it's a natural that I bring it up. It's sort of my baby. I created it as a Ruby implementation from scratch, but it's still not fast enough to see this really big jump that people want. And also, tracking CRuby is a very time-consuming thing. So I would like for it to be Rubinius, but I don't think it's the practical solution. Another one, JRuby, which is easily the longest running alternate Ruby implementation, taking advantage of the JVM. But the JVM is not for everyone. I think we've seen that we need to, it's unlikely that the Ruby core would decide to just pack it up and let everybody switch to JRuby. That doesn't seem likely. So given that, we need something else to do. So you might say, well, Evan, why do we need to worry about all the C methods? Let's just ignore them, and let's just compile all of the actual Ruby code. Well, let's look at what that might look like really fast. So let's just say we were going to take all of the YARV bytecode and turn that into machine code. So let's go ahead and let's take a very common, I wrote this down from memory, but we have all written something that looks exactly like this. Yes? Everyone's written something that looks exactly like this. This is effectively impossible to make fast with a very simple JIT. You get machine code that looks the equivalent of this kind of C code, which is a horizon that gives nothing to a compiler. It looks like a bunch of indirect calls. It gives us, the only thing that it would allow us to do is remove bytecode dispatch, and we still can't see through any of those RB-func calls. At best, it gets us maybe 20% speed improvement, but that's just because we've removed one bytecode dispatch. We haven't really improved much else. So, part 5. My proposal. The Ruby core library is very important. It's been developed since 1993, and it's where all of the work to make Ruby better goes in. It's where all of the new methods show up. It's where all of the bugs are reported to and fixed first. And efforts to rewrite that are hard because Ruby core wants to stay in there, and that's totally fine. So instead of trying to rewrite it and work against the momentum that the core library has, let's just instead work with it. So my proposal is that we do a thing called lifting the core. And what we do is we take all of the Ruby core library, all of that C code, and we convert it into a language that an actual JIT compiler can do. And the easiest thing to do there is with LLVM bitcode. And I should have put a definition of that in here. That is just an intermediate representation of the C code. It allows us to use the code within the Ruby core library as data. Instead of it being a static black box, it allows us to have the Ruby core library as data that we can actually use and optimize with. And as we generate more LLVM bitcode, LLVM IR, from the bytecodes, we now give a much wider horizon to a compiler to be able to optimize all of those things through. Because like I said, the C methods will just, every time it sees one, it will stop the optimization. And so it won't improve C extensions, but it could improve vastly all of the code that uses all of the core library. I'm getting ahead of myself on my slides, so I'm just taking a sec to let you read and take a drink. So here's my proof. Here's us going through this. So we've had this code before. And let's just say that we're going to go ahead and, rather than show you LLVM bitcode, which would be off the screen, and your eyes would glaze over even more than they're already glazed over, I'm going to do this in C. And it's going to be a C that would represent what a JIT compiler was generating. So we get something, we start off, we get something that looks vaguely like this. You make an array and you call enum min2. Now I've skipped a step here in that the compiler was able to say, hey, you were calling this thing on a literal array. So it's very easy for me to figure out what the actual implementation of this is. So there's a missing RB-func call to enum min here. You'll have to bear with me there. So we're going to play the role of an optimizing compiler here for a moment, which I know is something you all were really hoping to do at this conference. So we see this line here, a call out to enum min. Now if we were working only from compiling yarv bytecode down to LLVM IR without the actual core library available, this is where we would stop. We would basically end our work here, and we wouldn't really be getting very much out of it. But because we have the equivalent of something that I've left out some gaps, pretend there's code in there that the compiler can see. Now what we can do is we can say, okay, we know the definition of this function, and it's only called this one place, and it's actually at the very end. That's even better. So let's actually just go and dump it in there. Let's replace the whole thing in there. And so now we see that we also get all of these nice little constants, arguments that have been predefined to certain things. And so now we can do a thing called constant propagation, which is a big word for a very easy concept. Just put that thing in that other place. Right? So now we went from a bunch of variables to calling with a bunch of constants, and that's great. Because then we can do things. Now we can do things like, oh great, we're actually calling RB scan args with a bunch of constants, except for the pointer, which is effectively a constant because we know where it's pointing to. So we can do things like, well, we can inline all of RB scan args and do exactly the same thing again. RB scan args, if you've ever looked in it, is probably 500 lines long. So I did not include it on this slide because Again, your eyes would glaze over. But you can trust me in that what would happen as the compiler pushes all those constants through is that it turns into this. Isn't that nice? Because it can do all of that work. It can see all of the evaluations that you were doing at compile time because it's got all of the values. It's got all of the things as constants. And then you're saying, okay, well, we can keep going. We just do this same thing. We see that we've assigned this here, and we say, oh, hey, we can go ahead and just plunk that down in where it was used and remove its definition. And then we say, hey, we're calling nil p on q nil. That's a sort of silly thing to do. Well, let's just not bother with that. And then we say, hey, we said if not true. And that's also pretty silly. Let's just get rid of that altogether. And so now we're getting somewhere, right? And now we are going to, I didn't include the definition, but now we're back at that same step we are before. Hey, look, we've got one function call at the very bottom of this thing. Let's just inline that whole thing again so we get something like this. Oh, this also was inlining RB new from args as well. So we're starting to do some more now. So now we're inlining more. So now we can see things being set inside the array. We can see all of the bodies of basic. And we can also see, hey, there was no block passed. Remember, we knew exactly what it looked like. We know there's no block there. So we know that that's going to be false. So we can just remove that altogether. Super. So, but now we get this very interesting case of this block call. And I've started because it's going to be a very important piece. It's the piece that's missing from this whole equation. It's the piece that we, if we're going to go down this road, are going to have to fix. So I'll get to that in a sec. But what I can tell you is that once we do that piece, we'll be able to see that the compiler will be able to see that, you know what, obj in this case is an array. I've created it just lines above. And so when I'm calling each on it, I can know that, hey, I was just calling array each. I know array each. I can totally manage that one. And so what you get is something that looks like this. Great. So now we've got just a loop, just a for loop. Right? And we can also say, hey, you know what, we're doing array len on this obj, and we actually created it lines above, and we only put two things in it, so I know for a fact that it's a 2. And then you do another very classic thing, which is you say, you know what, I don't need to do a loop for two things. So let's just get rid of the loop altogether, and let's just do the two things, just one and then the other. And then you might say, you know what, we're referencing that array that we did before, but didn't we just put those things in there? We don't need to do that. Let's just replace them with the things that we put in there. And now, this is the definition of min I. And so, you know, we were just calling min I over here just 2 times. So let's go ahead and inline it and then do exactly the same thing that we're doing, replacing the constants as we go along. So we get some code that looks effectively like this. The first iteration went through and it said, okay, well, you know, we were just setting it. And the second iteration went through and said, oh, let me just compare this to the thing before. So the important part here is, again, this func call. Just like the RB block call, it's the piece that, if to make this work, you have to add the profiling there. You have to be able to see through this thing. And in this particular case, it's easy to see that it's a 2. I is a 2. And I'm calling the spaceship operator with val I, or UI val. And I just stored a UI val right above. So first of all, the first thing I can do is just say, you know what, I was calling the spaceship operator on a 2. That's just a thing called num comparison. That's not the exact function, but you guys got it. And then I can see, you know what, I've got these 2 values, I just stored them. I'm just referencing them as variables. We do the same thing that we've been doing this whole time, which is like, let's just dump them in there. We don't need to actually be doing that kind of stuff. And now we're doing number comparison on a 1 and a 2, and that's pretty obviously just a 1. We've got that, right? And then we just keep going down this loop. We see this, we see, you know what, we're just doing a 1, just these 2 things, and we know that that's just going to be false. Great, let's just get rid of some code, right? The compiler's just refactoring this for you, like a first-year student, right? And now it's like, oh, there's all this extra redundancy. We're not using any of these variables anymore. Let's just get rid of those. And then we see, okay, you know what? We're assigning this thing and pulling it back out. Again, totally unnecessary. And then we see, you know what, this definitely isn't equal to QUndef. I literally assigned it the line before. We don't need that anymore. And then, well, okay, you know, I don't need to set in a variable. I can just return it. Great. And then we get to this point where we're like, you know what, there's all this code above that's just setting up an array and assigning to it and allocating a thing. That seems stupid. Let's just get rid of that too. And now we're in business. Because remember what performance was? The same amount of work with less work. So the whole point of having the JIT is removing the dynamic aspects. And those two things that I starred are the most important things. They're effectively the only things that we would need to add to this whole equation in order to have a JIT, which is having profiling at those two calls to know what those two types were. So we can even add caches to the actual C code, and we can do different things. And as I was writing this, I realized, you know, if we're already having these tools that will read in the code, why don't we just have some tooling do it for us? So we can even have tooling that runs on the actual core library that finds all those places and automatically injects new code to keep track of the profiling. So individual developers don't even have to worry about remembering to add those profiling sites. The tooling that compiles the code for them will do it. So it's easy on developers. All of the Ruby core, everybody that works on Ruby core, on the core library can continue to just treat it like they always have, just writing the C code, doing the dynamic aspects, and all of the tooling will go in and just retrofit it to be able to have it used as an actual JIT available code. And because of that, and this very practical nature, I've decided to come up with a new term. I think it's very fitting given how Mats runs Ruby. MIPSwap. It doesn't have the same ring to it, does it? And it stands for Mats is pragmatic, so we are pragmatic. Mats, one of the best things about Mats is that he moves slow. And some of us wish he would move faster, but it's great that he moves slow on things. It's a very pragmatic move. He said that with Ruby 3, he doesn't want to replace everything. He doesn't want to completely start over because that will just set everything back. We need to be pragmatic and move forward at a careful pace. And one of the practical aspects of this is that it doesn't really require much research. All of the research in order to do this proposal is already done. We've got LLVM, we've got a compiler, we've got all the literature about how to use the caches, we've got all of the stuff. We don't have to go and invent new paradigms in order to do it. All we need to do is have the will to want to do it now. So like I said, we've got all the components, we've got the core library, we've got LLVM. It's easy to convert. You just need to write the code to convert the bytecode into IR and add a few hooks in different places. And I think now is the time to do this work. I want to see Ruby move forward now. I don't want to see it languish for years. And I love research. I love doing research and finding new ways to do things, but I feel like that has been done. I feel like now is the time to act on what has already been done and move up a level. So my conclusion, 3x Ruby 3 is going to be hard. It's not a simple thing, and I can tell you that when people say Ruby 3x3, I can guarantee you that every Rails developer wants their Rails app to be 3 times faster. And we may say, well, that's an unreasonable expectation, but is it? Could we do that? Do we have the tools to be able to do that now? And to do it, we have to remove the dynamic aspects of Ruby at runtime. And we've seen, we all just acted as a dynamic optimizing compiler. It's possible. C-Ruby is used by a huge number of people and companies. I would bet that billions of dollars moves through C-Ruby apps every single day. And think of the things that we could do for them by adding this into C-Ruby and making it 3 times faster. And we can take it to the next level. And I don't think that we should delay. I think we should begin this work as soon as we can. Thank you.
Yeah, thank you, Evan, for perfectly technical talk. Yeah, I really, really appreciate. So we have a little bit more, 3 minutes for questions. Any questions? Quick questions. Yes.
I'm worried I blew everyone's mind.
So just to be clear,
Yes.
your idea would be that when you actually ship Ruby, you'd just be shipping the LLVM bytecode for the actual interpreter bits and bobs.
No, probably not. So what we would do is we would compile the core library as normal. Maybe either we, at compile time, add the profiling in, or it's added in statically, whatever that is. But we compile that, and that's actually available as a, again, delivered to the end user as an executable in this particular case. But in addition to that, during the compiling of Ruby step, we take in the core library and convert it all into bitcode, and then save that bitcode actually within the binary itself. So the LLVM, as it boots up and has available to it all of the core library saved as bitcode. So you have 2 copies of the core library, the normal compiled version as you see it today, as well as a bitcode version of it that the JIT compiler can use when it wants to use it. That's, at least if you ask me to spitball, that's what the answer is.
Thanks.
Sure.
Anyone else?
I will answer questions about things unrelated to this talk, if you'd like also. Puma questions, or... That's fine. You got me here for 3 more minutes, so...
Thank you for having an interesting talk. I think I recognize you as a Ruby Central organizer guy.
Yes.
So because I've been attending the latest camp a couple of times. So what do you think about the RubyKaigi compared with the other conference you're holding, such as RaceConf or RubyConf?
It's great. I think it's the exact same quality. I love coming to RubyKaigi. I think they put on a great event. So.
Thank you.
Of course. Thank
you.
And you do it with all volunteers as well. I have people I pay to do it, so.
Yeah, we're jealous.
So perhaps I missed something. What if at runtime array min is changed?
Sure. So if you changed array min at runtime, so you have to do one of 2 things. Either it's changed to Ruby code, which is most common, and in that particular case, it could be optimized just like normal. If it's changed after this code is compiled, then you have to put in checks to make sure that min is what you think it is. But those guards can be very cheap. I didn't include it because it would confuse even more than I was already being confusing. But above that constant would be itself just one more check that would say, if this number is still that number, then go ahead and return the 1. Otherwise, go do the slow thing. So.
I see. Thank you.
Yep.
Okay, the last question.
Better be a good one, Charlie.
Oh, it's good.
Okay.
I was just wondering, I have never... we've talked about this approach and about using bitcode and stuff like that. Has anybody done it?
No.
Okay, that's what I was thinking.
I mean, I wasn't going to spend a bunch of time doing it if nobody wanted to do it. This is my proposal. I have done it in small scale. So I've written a couple of just, like I want to write a JIT, let's just see how I can do this, and code up in fact, I have a blog post from 2007 that still gets comments on it amazingly. That's basically how to do this very similar kind of thing where you compile like functions that are your operations, like an add and a push or whatever, as actual C functions, compile them to bitcode, load them back in, and then allow it to optimize. So, I mean, I've done it in small scale. I don't see any reason it couldn't be applied at this scale. So.
笹田さんご質問とかどういいですか？いいですか？ Okay, so okay, the final question from Koichi.
So thank you for great presentation, and so I love your ideas. One concern is so memory consumption. So maybe the code is explosion with this idea. So how do you think about that?
It is a worry that, about using more memory. But I think that you can run a JIT compiler in a way that that it can constrain itself with memory as well. So it could decide to only compile certain like methods after they get very, very warm or very hot that are actually very well used. It could also decide this method hasn't been used in a long time. I'm going to go ahead and free it from memory. So you can manage the tension of memory memory usage. It will use more memory, but I think that if, as I recall, the resident size of existing like Ruby 2.2 is just loaded without the heap is probably 20 megs or something like that. So that's just in the actual code bits that are actually stored on disk. So if the JIT itself generated another 20 megs worth of actual code, you can imagine that's as much code as already in there. So that itself is quite a bit of code. So I don't think it would be a huge explosion of code, but we would have to find out, I think, right? But I think we could do some back of the napkin calculations to figure out what that might look like. So
Thank you.
Thank you. Thank you, Ivan, for a great keynote.
thank you.
We loved it. Thank you.